All right, folks, it's Bass Action back in action here. We are finally wrapping up chapter 4. That's been a huge chapter for us. We're down to our last section where we're going to start to take away all of the hints that we've given you in the past. So we're going to give you some tools for how to handle solving polynomial functions when they don't give you any hints. Okay, so the first one that we're going to look at here is called the rational zero theorem, okay? And the rational zero theorem, first, the thing that you want to think about is that a rational number is simply a number that can be written as a fraction of two integers. So think two whole numbers written as a fraction, even if one of those whole numbers is 1. So even just a whole number, 1 is considered a rational number because it's 1 over 1. So remember back on one of our other pages of notes where we talked about how the solutions of a function can be broken down between real numbers and imaginary numbers, and then our real numbers are broken down between irrational and rational numbers. So what we know is that a polynomial doesn't have to have rational zeros. They could all be irrational. They could certainly be imaginary. But if a polynomial has any rational zeros, so the real numbers that are rational numbers, that means that those zeros for the polynomial have to come in a particular form. Okay, so what we're going to do is we're going to look at this idea of P over Q, and you probably talked about this in your Algebra 2 classes, but we're going to review it here. It's going to tell us that P is a factor of the constant, and our Q will be factors of the leading coefficient. So we can write that out here. So we're always going to be thinking about this plus or minus. Positive or negative could work on any of these. And the numerator will be factors of the constant. It's that last number that you'll see. And Q will be factors of the leading coefficient. Okay, so if we want to think about this idea, we can actually come down here and we can look at example 1. I'll come back to the intermediate value theorem in just a moment. Let's look at example 1. That's going to address our rational zero theorem. So what this theorem is saying is that if I look at this polynomial here in example 1a, if this polynomial is going to cross the x-axis, which of course it's a degree 3, so we know it has to at some point, if the 0, the place where it crosses the x-axis, is going to be a rational number as opposed to irrational, then that number has to be of this form plus or minus P over Q. So we can narrow down the whole possibility from the entire gamut of all real numbers, that infinite bucket of real numbers. We can narrow it down to what kind of looks like a lot of numbers to us, but is in reality actually kind of a small list. So what we're going to know is that we'll have plus or minus, and we are going to be thinking about factors first of the constant, and my constant here is 30. So I'm going to think about my factors of 30 divided by the factors of my leading coefficient. Well, my leading coefficient on this problem is just this 1, so I don't have to worry about anything complicated. So I'm just going to start thinking about factors of 30, and I'm just going to mentally go through those, okay? So I'm going to say, is 1 a factor of 30? Well, of course it is. Is 2 a factor of 30? Yes. Is 3 a factor of 30? Yes. Is 4 a factor of 30? No. So I don't list it. What about 5 and 6? 7, 8, and 9, of course, get rejected. Those aren't factors of 30, but 10 is. 11, 12, 13, 14 get rejected, but 15 is a factor of 30, as well as 30. So what this is saying is that this polynomial, where it crosses the x-axis, that if it is a rational number as opposed to irrational, it has to be one of these numbers. It could be a positive or negative, but it has to be one of these numbers. So we've taken the bucket of infinite possibilities and narrowed it down to 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 possibilities. Still a lot, but certainly less than infinity. So on our next one, what we're going to do is we're going to look at factors of the constant. So 4. Okay, so we can think about what are the factors of 4? Well, that's 1, 2, and 4. And then I also need to look at factors of the leading coefficient, 18. So as soon as we get a leading coefficient other than 1, our problem gets really kind of messy. Okay, and our factors of 18 include 1, 2, 3, 6, 9, and 18. And now we're going to start writing those as fractions. So you need to kind of develop a process for yourself that works for you. So I've got plus or minus. And what I like to do is I like to take each of my factors of my constant and individually put them over each of my leading coefficients. So for example, I'm going to take 1, 2, and 4 and divide them by 1. So of course those are easy. It just gives me 1, 2, and 4. And now I'm going to take 1 over 2 and 2 over 2 and 4 over 2, and I'm going to reduce each time. So 1 over 2 is going to give me a nice 1/2, okay? 2 over 2 is 1, and 4 over 2 is 2. Those are already in my list. So now I can continue. I'm going to take each of these, dividing them by 3, continuing my process. So now I'm going to have a 1 over a 3, and I'm going to have a 2 over 3, and I'm going to have a 4 over 3. Continuing on to 6, I'm going to have 1 over 6. 2 over 6 reduces to 1/3, so I don't need to list it again. 4 over 6 reduces to 2/3, so I don't need to list it again. Moving on to 9, I'm going to have 1 over 9. I'm going to have 2 over 9. And I'm going to have 4 over 9. And then I'm going to have 1 over 18. 2 over 18 reduces to 1/9. I already have that in my list. And 4 over 18 reduces to 2/9, and I already have that in my list. So again, if this polynomial is to cross the x-axis at a rational 0 as opposed to an irrational 0, instead of having to think of the entire bucket of infinite possibilities, I've narrowed it down to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 times 2, 24 possibilities. Again, it's not a very attractive list, but it certainly is a much better list than the bucket of infinite possibilities. Okay, now let's take a look at the intermediate value theorem. So let's go back up here to the top of our notes, the intermediate value theorem. Okay, now the language on this one might be a little bit confusing when you look at this at first, and it says that if I have some polynomial function, okay, so I have some polynomial function, and if a is less than b, okay, and f of a and f of b are opposite signs, okay, so that means these are y values. So I have some x values, and these are y values, and it's saying that if my y values are different signs, then there has to be a real 0. Now, let's just think about what this looks like. That kind of helps break this down for us. I'm just going to draw in a random polynomial function that crosses the x-axis. So I'm just going to sketch something in here. I'm just randomly drawing something here. Okay, so I've got some polynomial function here, and I can see that it is crossing my x-axis. So what I'm going to do is I'm going to pick an a value over here, and I'm going to pick a b value over here. So now I've satisfied this requirement that a is less than b. Now that means that I have a point right here that is my f of a. Okay, and I have a point right here that is my f of b. Okay, so we can see now that we have a is less than b, and I have f of a here and f of b here. Now what I can see from my graph is that my f of a is a positive number. It's above the x-axis, and I can see that my f of b is a negative number. It's below the x-axis. That then meets this requirement that f of a and f of b are opposite signs. So what this is saying is that if my A is less than B and my Y values change from positive to negative, then the graph must be crossing the x-axis somewhere between those two x values. Okay, so this is saying that it crosses. So just being able to see the change in signs of the y values indicates that somewhere that polynomial has crossed the x-axis. So now let's combine this with our rational zero theorem. So let's continue to the bottom of our page. So the first thing we're going to do is we are going to come up with our possible rational zeros for our p of x polynomial. So I'm going to pause this. I'm going to let you practice that example 2a. Come up with the possible rational zeros for p of x. Okay, so check your answers. Did you get the same possible rational zeros for the polynomial as I did? Now, remember, it's not saying that these are definitely going to be one of the zeros. It's just saying that if one of the zeros is a rational number, it has to be one of these. Now, the intermediate value theorem will sometimes ask us, in the next page we'll get a little bit deeper into this, but it might simply ask to show that there is a zero on a particular interval. So what we're going to do when it gives us one of these intervals, okay, let's say this interval of -1 to 0, is we are going to evaluate our polynomial at the two endpoints of that interval. So for example, we would find f of -1 and we would find f of 0. So I'm going to pause this. I want you to evaluate our polynomial at each of those. Okay, so let's check our answers. At f of -1, the polynomial evaluated to 10, and at f of 0, the polynomial evaluated to -6. The reason this is significant for us is that 10 is a positive number, and -6 is, of course, a negative number. So, since we switch signs, we know that our graph had to cross the x-axis somewhere between -1 and 0. Now, why is that useful for us? Because when we look at our possible rational zeros, the only number in this list that's between a -1 and 0 is going to be a -1/2. So this -1/2, written as the negative, if our zero between -1 and 0 is rational, it has to be -1/2. So let's write that down so that we can kind of keep track of our thought processes here. So we are speculating that -1/2, well, we know that -1/2 is between -1 and 0. So we're going to test and see if that actually turns out to be a 0 for our polynomial. So let's set up our synthetic division. I'm going to pause again. I want you to do your synthetic division with a -1/2 and see if you get a 0. Okay, we can see that when we evaluated at -1/2, we did in fact get a 0. So now what we can do is we can take our remaining polynomial and we can set that equal to 0. So 2x squared plus our 10x. Sorry, that looks a little messy there. Plus our 10x minus our 12 equals 0. I'm going to divide everything by 2 here. So I'm going to have my x squared plus my 5x minus my 6 equals my 0. I'm going to go ahead and factor this. So I have an x plus 6. And then x minus 1 equals 0. So I get x equals -6 and a positive 1. So what we can see is that we have now found all of the zeros for this polynomial. And not only did we find all the zeros for this polynomial, but every zero that we found was a rational number in this case, and all of them came from our list, which is exactly what we wanted. If we got to a 0 here that wasn't listed here, then we must have made a mistake someplace.